All right, so for weighted averages, what I was saying in the last video was that the isotopes aren't equal. There's lots and lots of different types, but there's one that's the most stable, and that most stable one is going to be the most common. So if we take a look at carbon 12 is the most stable out of all the carbons. So it is the most common. And that is why the mass of carbon is really, really close to 12. Now, right here, this is what's called a percent abundance. Now, out of majority of the carbons that exist, 98.89% of them have a mass of 12. 1.1% have a mass of 13, and less than 0.01 have a mass of 14. So all the other ones that you see, they're less than a 0.01. Excuse me. They're less than a 0.01%. So we can kind of ignore them in the calculation, but let's just say, how do we actually do this calculation? What you would do is you would turn this percentage into a decimal. So you do that by dividing by 100. So it becomes 0.9889. You do the same thing with this one, divide by 100. So you get 0.0111. And then this one over here, divide by 100. And you get 0.0001. All right. Now, what do we do with these? Well, you now multiply by the mass that's with it. Times 12, times 13, times 14. You get your values. Here you get your values, and then you add them up. Now, I do not have, oh, I do have a calculator. Yay. I was going to say, whoopsie daisy. Got to record this video again. Well, let's check it out. So 0.9889 times 12 gives you 11.86. 86, or we can say 87, since we're rounding up a little. And then over here, 0.0111 times 13, and we get 0.144. And then finally, we have 14 times that 0.0001. Oh, that one we should have just been able to do that in our heads. Why did I? All right. Now what do? Well, we add them up like we would an average. So 0.0014 plus 0.144 plus 11.87. Now this is equal to 12.01. And the units you might see written are a little u. It's a tiny little u. Or if you used grams, you'll eventually see grams. But for now, since we're dealing with isotopes, you're using the atomic mass unit, or AMU, sometimes just written as U. Not U as in you, U as in the letter U. All right, now that's how you calculate atomic mass using the percent abundance or relative abundance. All right, now one thing I want to show you is a mass spectrometer. Mass spectrometers are a very, very, very important way of detecting different types of particles. So if you go on to higher level chemistry, or if you choose to develop a career in chemistry or want to be some sort of scientist, what your main focus should be is really how to use instruments. A lot of companies care for scientists that have a very specialized skill. So if you know how to use very, very expensive instruments, you'll have some job security. But that's a little you don't normally get that expertise from just getting a bachelor's degree. You usually get that expertise from going into a master's or a PhD program. All right, but that's a whole different topic. If you have questions on that, I can answer some during class. But let's talk about what a mass spectrometer does, right? A mass spectrometer is basically, let me see if I can, a mass spectrometer is a separation technique. It's like chromatography. It's separating things based off of their size. Well, if you think of atoms, right? Atoms are different from each other. Some are bigger, some are smaller, some are more massive, some are less massive. So, how do you separate them? Well, you can't have a tiny little filter, right? If you've used like something to filter out, like in your cooking, right? You have these little mesh filters with tiny little holes. You can filter out like solids from liquids, but with particles, we don't have that option. So you have to get a little bit more creative. So what happens here is you have a large particle, right? Let's just say you have a large molecule. It looks like junk, but that's the point. And this particle gets heated up, extremely high heat, that it breaks apart this compound. So now instead of having a large compound, well, now it's broken up into fragments, it's broken up into pieces, it's broken apart into its components. And now this thing is sent out and pushed through as a beam, and it's accelerated, right? And what happens here is, well, now it's got a charge. These little pieces of mass have a charge. So maybe a tiny little fragment has a little charge, or other little fragments have their own charge. And they get launched, and you have a magnetic field. And what this magnetic field does is it applies a force to those particles, and it begins to separate them by something called the mass to charge ratio. Z is the charge and M is the mass. This is kind of how they discovered the mass of the electron. If we go back, it's by, well, they first discovered the mass to charge ratio of the electron. Then once they knew the charge, they were able to discover the mass. But this is the same concept as it, or a very similar concept, where the large particles, if they get attracted, they're going to get pulled to the same side, because the heavier ones are going to go to one area and the lighter ones are going to go to the other. So now if you have a detector plate, you know that some beams hit on one side, they're going to be smaller fragments, and if they hit on the other side, they're going to be larger fragments. Now, this you will go in more detail as you get a better understanding of chemistry, but this is just the basic fundamentals of how this equipment works. It's by separating from a mass to a charge. So it does that, little review. It breaks apart the sample, ionizes it into a beam, so a beam that has a charge. It passes through a magnetic field, and that magnetic field is going to affect, based off the mass, based off the charge, and then that's it. All right, you'll see little graphs. Let me see, little graphs. I don't think I can show you. Little graphs in your book that'll look like this, right? This little table right here. They'll look not like the bar graph. They'll look like this. So what happens is the ion beam intensity, how high the peak is, will tell you how many of those particles have that mass. So you'll see that majority of the particles have a mass number of 20. And Well, the percentages we learned earlier with that carbon, right? Well, this is where they come from. They have a percentage here. Well, so they'll call this a value, and they'll find the ratio between these, and that's how they determine those percentages you saw in the previous slide. So like carbon with 98 would have had a peak really high around 12, and it would have had a super tiny peak around the carbon 14 or the carbon 13. All right, so the ratio of these peaks will tell you the percentage, and then from there they'll make these little bar graphs that are used to count the number of atoms. And I'll teach you how to read these graphs a little bit later, but I just want to talk to you about the beams. This graph is more important than this graph. Okay, this graph is like a simplified version. You'll see more of these in like on your tests, but this one right here, if you can get some understanding of this, it'll help you in OChem when you start learning about the other types of graphs and the information you can get from there. Okay, but oh, Pika, excuse me. All right, where were we? All right. Okay, where were we? Oh, I think Pika muted my mic. Come on, go. What? Stop. You're stressing me out, girl. All right, so, come on, Pika. Here, come here. Let's go. Sorry. All right, so we got that 62.6%. We don't write it out in percentages. We like to write it out at a decimal, 0.6260. And then we write that 37.4 in the same style in decimals, right? We do that by dividing by 100. We multiply it by the corresponding mass. So the corresponding mass was 186.956. And the corresponding mass for that one was 184.953. We multiply across, and what I like to do, I like to make sure my numbers make sense. So since this one has a higher percentage, that one should be the higher value. All right, so just always try to do that. It'll save you a lot of mistakes. Always think of what the number should be. Try to round off in your head, and just practice doing that, and you'll get significantly better at doing mental math. So 0.374 times 184.953. Pretend that's a 9 and a 5 and a 3. And then we end up getting 69.172. and it's 5, it should be 6 sig figs. Whoops. Let's pretend we had another one over there, but oh well. All right. Let's add these up. So our answer should be really, really close to 186 because that's our highest percentage. So 117.03 plus 69.1724. And our answer here is 186.202 AMU, atomic mass unit. All right, so that is the average atomic mass. Now, which element was that? Let's do a little quick check. 186. 186 looks like it's rhenium right here. Yeah, it looks like it's that one. So there you have it, folks. So that goes to that. So take a look at what we've just done. We just determined the identity of an atom by knowing the mass and the percentage of that atom. So that machine that I just talked about is very, very good at identifying unknown substances because it will give you the percentage of your substance and it will tell you how much it weighs. It's not going to say this is bromine, this is tungsten, this is your element. It's not. All it's going to tell you is there's a particle with this mass and this is the percentage of it. All right? So that machine is so useful in detecting, like, let's say, chemical waste. Let's say I'm a giant evil corporation who doesn't care about the environment. So in order to save money, I dump my, like, let's say, cobalt waste into a water source, or I store it and I pretend I store it poorly. All right, let's say I like saving money, so I cut corners everywhere. Now, what I would do is I would send this trash to the environmental waste people. All right, and they'll go put it in their landfill. And let's say it rains and it gets my poorly stored chemical waste and it brings it into the groundwater. And now the nearby people to the landfill are going to be drinking that waste and is going to make them sick and die. Now, in order to prevent that, what the state does, it hires people to check that water. When they check that water, they run it through one of these types of machines. And it tells them the types of particles that are in there. So if you start getting some heavy particles, some heavy atoms, well, you know that the heaviest atoms, right, are no good for us. If you start looking at like these right here, they're not good for you. They're not good for you at all. So once they start seeing those detectors, they know that those signals being detected, they know that waste is bad waste, that it was not disposed of properly, that wasn't properly treated. So they're going to come after my company because they know that my company has that type of chemical waste. So this is actually what happens in modern day. This is one of the ways that they regulate the environment. So that machine, very, very useful. You can also combine it with other things. We're going to talk about that later on. But I believe that's it right now. This is a long video, but you'll learn stuff.